Good morning. We're starting today with a review of Chapter 8, which is on math functions. This chapter is the last chapter that we really concentrate on a specific type of instruction, but we're going to concentrate on the math instructions for this chapter. And this is a chapter that shows how you can tie math instructions into logic, and it's a very interesting chapter in that now that you're fairly good at relays, timers, and counters, and we're going to add math logic and math to the logic, and that's what this chapter is basically about. So there's two types of math instructions. The first is the comparison instruction, and this is a view of the comparison instructions. There's some of them that are found inside the Siemens processor. Allen Bradley has a similar group, and these instructions are, you can equate them to contacts, normally open, normally closed contacts. They'll let power pass through them if there's a condition that is met. In other words, if one thing is equal to something else, if one number is equal to another number, if they're not equal to the one to the other, if one is greater than or equal, they'll let power pass from left to right. And this is a powerful function in that you can now mix contact or digital logic with the greater than the comparison statements. So these are comparison statements that act just like contacts. If you picture them as contacts, that's all they really are. And they look a little different in that Allen Bradley uses a block like a square, and Siemens uses more like a contact, which is really what they are. But if you just picture them as a contact, then with the satisfying of what's going on inside the contact, you're in. That's the basis of this instruction. So this one would be if it's equal. And what is it? If it's this number in1 is equal to this number in2. So if this is equal to this, boom, you go left to right and you're passing power. And most of these, the EQU, the NEQ, are the same mnemonic, if you will, for Allen Bradley and Siemens. And there's a number of these, and they may be a little different, test a little different. Some of them are exactly the same, and they're kind of interesting. But if you need these are available, and if either Allen Bradley or Siemens, they're there, and they're very powerful instructions. So we're just going to kind of go through them just a little bit. Now this is the other type of instruction. This is the instruction that allows you to do math, and if you look at it, this would be like a coil. This would be like an output. So if you have some logic, then at the end of that logic you get to do some math. And this is the various ones that you can have. These are typically in boxes or blocks, and if you want to do more than one thing at a time, for Siemens, use the calculate block. For Allen Bradley, use the compute block. And if you want to remember the difference between the two, if I was with Allen Bradley, I'd say compute till you puke. That's how I remember compute is with Allen Bradley, and calculate is the other one, and that's with, they both start with C, but that's the one with Siemens. So if you see I want to do more than one thing, if I just wanted to add two numbers together, if I wanted to do some add, multiply, square root, any of that stuff as a group, you would use this combo block, which is a much more powerful block than these other ones. And you say, well, why would anyone ever want to write with these other blocks? Well, if you look at the evolution of the processor languages, the various PLC languages, you'll see that they did not have these combo blocks until much later. They would have an add and a subtract block. And for a long time, they only allowed you to add and subtract and multiply and divide integers, which is a real painful process. So they gradually moved forward with their instruction sets. And if you find somebody that's copied something from an old program, you might find that they actually did this multi-step, where you do some adds and then add those together and that type of thing. Or you might find that they just used the calculate block or the compute block, and that's all they ever did. So as you're dating the evolution of these programs, you might say, that's somebody that wrote a program 25 years ago, and then today he's copied it over, but he didn't want to mess with the flow of the logic, so he just used the same logic. Otherwise, most people would automatically gravitate toward these combo blocks. So this is an example of the calculate block. And as you look at it, here are your inputs. Now, this is the actual values that are going to be executed in this block right here. These are the numbers that fill in these blanks. So these are the numbers that come over and fill in these. It's like fill in the blanks of these. So N1 would be the number that is in this pound sign IN1. The number of this IN2 would be the number that's in this double wide or 32-bit integer right here. And this is another one. It would be a double 32-bit integer right here. Now you notice that Siemens makes you declare the type of variable that is going to be the output over here. So in other words, this guy has this to check against this. So if this is not a 32-bit integer, this instruction will not work. With Allen Bradley, they'll let you do it. And you don't have to do this double check over here. Is this equal to this? If this is not a dent, this better be the same as this. Siemens does that, Allen Bradley doesn't. Now, which is better doesn't really matter. You'll just notice that that's a little difference between the two. So we're going to go down through here, and modulo is the remainder after you've done an integer division. Absolute value makes it a positive number. Min and max compares two values, finds the minimum of the two. Floating point. Now, most of these instructions can be executed in a floating point as well as integer, and you always want to use floating point if you can. So if there's a possibility of integer or floating point, always use floating point, because it carries with it a decimal point. Now, when do you not use floating point? Well, if the things that you're using are integers. And another thing you do not want to do with floating point is do a comparison against 0, because even though your floating point number you would imagine was 0, it might be just slightly off of 0. And if it is slightly off of 0, it will not do it will not give you a result of 0, therefore your comparison statements will not work. So again, if you are looking at when do you use certain things, don't use floating point comparing to 0. Compare it to 0.001 or something like that, but don't compare it to 0, because it will not, it many times will not work, and you'll be sitting there scratching your head as to why does this not work. But that's why. Okay, now in this chapter, we also quickly review the move instructions, which are they're good instructions to know about, but just realize that anytime you're dealing with numbers, then you're going to have to move those numbers to do certain things. So again, the move block or move instruction or masked move is a powerful instruction. We're going to repeat this in chapter 13, but that's something that you just need to know that exists. Scale and normalize are used by Siemens to bring in an analog number. We talk about this again in chapter 10, but if you want to bring in an analog number, Siemens allows you to do these two instructions, which then gives you a number inside your program that gives you the ability to, okay, what is the number, the raw number that's coming in? I don't want to deal with it as a number from 3,000 to 33,000. I want to deal with it as a number from 0 to 90, but it's in floating point. I want to do that. And that's the kind of thing that scale and normalize will do for you. So again, this is the Siemens approach. Allen Bradley lets you do the scaling as you configure the card for the inputs. In other words, they do it separately. They do it as you're configuring the card. Siemens does it inside the program itself. Again, we review the old SLC instructions, and then we look at them This would be an example of using, instead of the calc block, or compute block, excuse me, you would do add and then divide. And this would be an example of the way that it was done prior to the calc block being part of the instruction set. The comparison statements, some of the comparison statements, and again, this is the way the Allen Bradley SLC comparison statements looked. If the number that was in 720 was less than 50, this would turn on. If it was greater than or equal to, wouldn't. This is a comparison statement, then going to a subtract block. So you have compare and then math. Here you have logic and then comparison statements, but this acts just like logic, and then to an output. This is a mixing. Here's one with multiple statements, multiple compare statements, and they would be this or this or this, because it's in an OR fashion. Turns that on. The lim. Now this is the same for Allen Bradley and Siemens, and the old Allen Bradley and the new Allen Bradley. So if I have a lim statement, this would be like a pass-through. If the number in N720 is greater than 100 but less than 200, this turns on. Now let's say I want the not of this. You would do it just the opposite. The low lim would be the high number, the high lim would be the low number. So in this example, if the number is greater than 200 or less than 100, and that means it could go negative, then the output bit turns on. So this is the positive, this is the negative of that instruction. So if the low lim has the high number, the high lim has the low number, then it reverses. You say, could this be a variable? Yes, it could. So could you flip a high lim? Could you flip one to the other just by changing the number in the variable? Yes, you could. So this is an example of a comparison statement, and then if the number gets too big, you basically peg the number at a high input. In other words, this number that's coming in here can vary. If it gets greater than 3277, then I put 3277 into that number. So basically this lets you say, okay, I've got a variable that's coming in to my program, and if that variable goes higher than the maximum value that I want in my program, I peg that number at the highest value. And I set an alarm. So I go out and find out what that problem is. But I don't let the number creep above my highest value, because I don't want any number higher than the highest value, because I don't know what the results will be in my program. So this gives you an ability to take a number and guard against, this would be the low end. So in other words, I want the number in here to be at least 3277, and I want it to be no more than 16384. So if the number in I1.0 gets less than this or greater than this, I want to peg that number, and I want to sound an alarm. It guards your program from ever going out of range. On the other hand, you may, it depends on how you want to deal with it, but this is one way of guarding against the number going out of range and then sounding an alarm. Okay. Now this is an example of a comparison statement that might go awry. So basically this is a not good situation. So I have a set point here, and I want to do cooling on this. This stuff can get too hot. Whatever it is, it can get too hot. So if I go above 450 degrees, then I want to turn on some cooling. So the cooling comes in through this output O0.2 or O0/2. So if I get too hot, I want to cool down, then I can turn off that output, and comes back and keeps doing this like this. What's wrong with this? Well, It's not bad, but this on and off can turn into a problem in that if this goes real quick, it can make your equipment wear out quickly. In other words, just the mere act of turning something on and off causes your process to have a problem. So if you turn on a motor too often, it'll heat the motor up. Each time you turn on a motor, it have an inrush of current, it heats it up, and then it would stress the motor and it might make it burn up too quickly. So basically, you don't want to do this. Sometimes you can, but sometimes you don't want to. So how do you fix this? Well, this process right here is what? This is it's a memory process. So if you go above a certain value, you want to then go the other way. Now here's what you really want. You want to go above 450, turn on cooling, then come down to 400 or whatever, your lower set point, and then go back. So you want to do something like this. It's a slower, methodical approach, and let's say that you want to tighten it up. You basically raise your 400 up to 425 or something like that. But you want to have the slowness of this process as opposed to the quickness of this process. Well, how do you do that? Well, one of them is to move the set point. In other words, if I go above a certain value, move the other number into my set point. That's this approach. So my greater than now is this number here in 724. So if I go one way, I move this number in. If I go the other way, I move this number in. So that is a playing with the value in the comparison statement. That works. Let me show you another way that works. This way works as well. So if I go above 450, I turn on cooling. Then how do you turn off cooling? I go less than 400. This works as well. What is this? It's a memory circuit. This is just like the high and the low of the tank. This is the same thing, only now we're using numbers to turn it on and off. It's just a memory circuit. What's another process? Right here. This is a seal circuit. Look at this. This is a seal circuit. It does the exact same thing. So all these approaches are the same and they execute the same logic. But if you look at this as a memory circuit, you say, oh, I see, it's the same kind of circuit as we've had before in Chapter 6 with the high and low and the filling of the tank. It's the same thing. Now, in each of our processors, we have variables that we need to get at, and there's various ways of doing that. If you were in a microprocessor, they have a status word that you can look at that gives you information after you've executed a math operation. And the old Allen Bradley gave you this in this status word S:0, okay, and this various words right here. So S:0/0 was the carry bit. So if you had an execution of a math instruction, this would be set, this bit would be set after that instruction executes if there was a carry. Likewise, 0/1 would be if there was an overflow. 0/2 if there was a 0 as a result. If there was an error, it would give you S:5/0. Why would you need to know that? If there's a math error, in other words, if you divide it by 0 or something like that. Or you went over a high limit of your math, or you went under a low limit of your math. What would you do? Well, there are bits set sometimes that will actually stop your program from executing. Some programmable controllers do that. Other programmable controllers just let it go. Other programmable controllers kind of give you a warning and make you decide. Allen Bradley typically gives you a warning and will shut down in certain instances. The old Modicon did not. They let it go, and you would just be sitting there saying, why didn't my program work? And it would be saying, you dummy, you were dividing by 0, so I didn't execute that instruction. And you go back and you fix the problem and you go on your way. So either way it's just different philosophy, different people. So how do you get access to these? Today, that's the old style. Now, how do you get access to these today? Here's your status table for RSLogix 500. These have gone away. Where are they still at? Well, they're there. We'll just have to. They're in certain. We'll have to talk about where they're at. Okay, but that's the status table for the old SLIC processor. Okay. All right, so this would be the scale with parameters instruction, which is an Allen-Bradley instruction for a y equals mx plus b. So if you want to know how to execute a y equals mx plus b instruction, right here it is. And you say, why did they include this? Well, a lot of people do not get y equals mx plus b, and they are hard-pressed to figure that out. So this gives you a min and a max for your input, a min and your max for your output, the variable for your input and your output, and there you go, let it rip. Basically, this is the setting up of the y equals mx plus b format. It just allows you to set it up without having to calculate the slope and the intercept. So this is a form of y equals mx plus b that's been simplified, and that's exactly what it does. This is a problem that you do not want to have happen, and that is if you add a number and then it goes over the high limit. In other words, if it overflows, what happens? Well, this can shut down your program controller. This will shut down an Allen-Bradley. It will not shut down some of the other program controllers, but you have to set this as a something that will or will not shut down your program. You have a choice. You can go back into the program controller and say, I don't want a math overflow to shut down my program. Out of the box, most of them come so that it will. So you have to set this as something you want, but you do not want to do this. You do not want to have an overflow in your program, and that block right there will do it. Okay. So again, this is the status table for the CompactLogix processor, and this gives you these bits. Now these bits are control bits that you can use with a contact, and you can see if a certain action happened. Now these are found in the get system variable instructions. So you can find any of these if you do this. Use the help with the GSV instruction. So you can use these instructions like s:/fs. Now what is fs? First scan. So if you want something to execute the first scan of the program but never execute again, in other words, you went from program to run, or let's say that there was a lightning strike in your factory and your lights went off. Lights come back on, this executes the first scan, your program comes back on into running mode. FS, s:/fs. So you'd use that contact to set up things, to initialize things in your program. Okay. Now, how do you do that with Siemens? Well, Siemens is a little different, and they do an OB. An OB100 is the program that you go to, and if you have logic that you want to execute on the first scan only, you put it in OB100, and that will only execute on the first scan of your program. But you put it in a special OB object block, or yeah. Okay, so here's how to fix the problem up above that you had with the add block. You put a one shot in front of it. So anytime you have a push button, you don't want to add, you want to do this kind of thing right here. And that's standard. So this is a program that will add 1% or 5% to a number, and here is to decrement 1 to 5%. So if you want to push a button that says I want to make that button go up by 5%, right here it is. And this would be a variable for limit protection on a variable. Here's the compute block for Allen-Bradley, and as you notice, this is variables these are variables inside your program. That's with the SLC, but it's the same with the CompactLogix processor. Mixing of data types. Like I said before, Allen Bradley lets you do it, Siemens doesn't. You can mix any types of variables with Allen Bradley and they'll take it. These blocks will give you a result. It's the result of this type, but they don't make you commit to what type you want. Here's the compact instruction. Here's this compute block. Compute, here's the variables, and you notice these are variables that you've defined in your program. There's no block out here that tells you have to N1, N2, N3, N4. You don't have to do that. Here's your limit test with your newer one, the same as the old one. There's masking instructions, equals, not equals. So these are Allen Bradley CompactLogix instructions that compare to the other instructions that we just talked about. And these are the Allen Bradley CompactLogix math instructions. And there's a bunch more. You can go out to the right and you see a bunch more. And here's your move instructions. So where do we use these? Well, here we go back and we're now looking at the that juicing application we had before. Well, where's math involved in this? Well, if you look at events as states, we're going to talk about that in chapter 11, but you can use numbers, and I strongly recommend you use numbering of a state to give you a state. You use numbers to give you that logic, and if you look at it, you say, okay, if I'm in state 1, I'm in the fill operation. I'm in state 2, I'm in the condensing operation. If I'm in state 3, I'm in the drain operation. So you basically tie a variable to a number, and then that gives you the ability to, in that state, execute certain operations. And that's how you basically can go from state to state to state using numbers. So use numbers for states instead of relays. Here's another one. This is a paper making process. In this process, we put in material and a lot of water, and then we put it out through this drain pump to a manifold. The manifold then takes that sludge or slurry or whatever you want to call it and spreads it out over a moving chain. The moving chain then allows the material to start the drying process, or we take the water out of it. So you suckle as much of that water out as you can, and then you put it into a dryer, and in the dryer you finish the drying process and then you roll it up. So that's how you make paper, basically how you make paper. So if I add water and then I add pulp, how do I add pulp? Well, I have a loss in weight feeder, and I've got a loss in weight feeder down here that I'm going to show you in a second. This is my loss in weight feeder. So at the beginning of the loss in weight operation, I look at the weight. I say, how much is there in this program? So I look at the weight and I start at that point. So I'm shaking this box and I'm weighing this box at the same time. So I say, I want to take 500 pounds out of this box. How do I do that? Well, I look at the weight. It can be anything at the beginning. Let's say it's 5,200, and I want to take out 500. So I say 5,200 minus 500 is 4,700. So I want to shake this until the weight here goes less than 4,700. So I start and I collect my start weight, and then I look at my start weight and my active weight, and I get the amount dumped. And when the amount dumped goes over my target weight, I stop. So these are variables and these are math instructions, but they give me the ability to dump material out of a box. Okay. So this is another one, and if you want to know the way to do this back and forth, back and forth, back and forth, use numbers. So you would use numbers to do this kind of an operation. This is called a festooner. We also talk about in this chapter about numbering systems, and I do want to just give you just a little bit of an overview on this. So you can store numbers in a program controller in a number of formats. They're just like it is with any other computer system. You can store it as integers, you can store it as booleans, you can store it as floating points, and you can have long floating points or long integers. And you can have with Siemens, you can have a byte length integer as well. With Allen Bradley, you can't, but you can at least look at those octal numbers. We don't deal with octal, but you can display things in octal if you want to. But octal would be base 8 or base 8, and then you can also have hexadecimal numbers, and hexadecimals would be base 16. So you can view things in all these various, although basically you're dealing with integers. They do have a conversion process between BCD and integer. In most program controllers, you can do an automated conversion of that. So, how do you do basic operations? An add block. Okay, this would be an add block of 2 bits, a bit in one number and a bit in a number, and getting a result, and then getting a carry. This would be a half adder. What would this be? Well, this would be an addition of a number in one, an addition of a bit in another, with the carry from the prior bit. So did we have a carry? Here would be my result, and here would be my carry that would go to my next bit. So this would be a full adder. This would be comparing of numbers. You say, why would you ever do this? You wouldn't. But this shows you the ability to do carries and to do a full adder. So this would be an implementation of a full adder in ladder logic. You would never do this because you have the add block already. But if you had to do this, this would be how you do it. How do you do subtraction? Well, there's 2 ways to do subtraction if you wanted to do it bit by bit. One way would be to complement all the bits and add 1. The other way would be to move from the right to the left with your bits and bring the bit down, bring the bit down, bring the bit down, bring the bit down, until you've seen the first one. At that point in time, you bring that bit down, but then all the succeeding bits you flip. And this is what would be done by that. So you would start with, this would be my flipper bit. Then I would bring my first bit down. Then if that was a 1, I would set my flipper bit. From now on, if I've seen a 1, I flip the bit. Otherwise, I don't flip the bit. And then if that bit was a 1, I have to set the flipper again. So again, this is a 2's complement for 2 bits. You would repeat this portion of it 14 more times, or a total of 15 times you would do this portion, do a 16-bit 2's complement. You'd never do that because you just subtract, and SUB. This is how you do it with bits. Comparison with bits is a little harder because you always have to look to the farthest bit to the left, and the next bit, and the next bit moving to the right. And that's hard, but you can build it if you wanted to. This would be a building of a comparator with just straight bits, Boolean bits. Now we talk about Radix, and the Radix is the way that we view numbers, and you can see various radices here. It would be binary, octodecimal, hex, BCD, and ASCII. So you can display numbers in all different formats, and these are some of those formats. That's called a Radix, R-A-D-I-X. Okay, this would be Siemens bit access, byte access, and word access to a word. Okay. Should be how I can do comparison. Okay, now I'm going to ignore this first little piece right here, but if I have a bit, the .x0, .x1 would be the Siemens addressing, the .0, the .1 would be the Allen Bradley with the Logix processor, and the old processor would be the //0, /1, /2, and all that kind of thing. So here would be an example. I want a bit in a word. This would be bit 15 of that word. This would be the Siemens addressing. Take out the X, that'd be the Allen Bradley. Put in the /, that would be the SLC processor. And again, this is a chapter on numbers, and I'm not going to work these examples for you right now. But these are some problems that you might be interested in. And a lab that I'm sure that you've already seen. But if you have any questions, please email me and let me know. Take care. We're going to be working on exercises at the end of Chapter 8. So problems, end of Chapter 8. And we'll do a little bit of an introduction to the lab. So, number 1, write a rung to turn on a coil when the value in int 8 is greater than 20. So I do a greater than box, greater than box, and it's int 1 greater than 20. And then we go over to another box. It says, and this is an and, so this would be the 2 of these. And we would say int 2 less than 25. And that would give us a coil. So this would be an and. This would be an and instruction right there. That would be problem number 1. Problem number 2 would be when the value int 1 is less than 20, or, so this would be an or, the float 1 is greater than 8. So there's a greater than float 1 greater than 8. So this would be an or function. And that would give me a coil there as well. So that gives you some ideas how to work these. Problem number 3 would be the same. I'm not going to do that one. You can do that one. And problem number 4 is a multiply block. And basically it would do this. A mul. And the first value is int 1 multiplied by 10 and result. Okay. So you may, this times this goes into here. Same with the divide, a divide block number 5. Divide the contents of int 4 by 4 and store the results someplace. Okay, so number 6 is a little bit different. In this one, we're asked to, instead of 6 timers, like we did before, just using 1 timer, how would you do this? So basically with 1 timer, let's say we go for 30 seconds. So TON, that turns itself off. This would be the done bit, would be the, let's call this the coil out here would be A. When it's done, the not of A. And this would be a TON timer. And let's call it timer 1, okay? Timer 1 has an accumulated value. Right here would be the timer 1 accumulated value. Or if you're Allen Bradley, T1 dot ACC, however you want to do it. And then you would say if less than, or the less than symbol, your choice. This is Siemens, less than is Allen Bradley, same thing. T1 ACC is less than, and remember this is in milliseconds, so let's go 5,000. That would be my first light. So you're looking at T1 ACC less than 10,000, but greater than or equal 5,000. That's my second light, etc., etc., etc. So I move every 5 seconds, I go to the next light. And I just keep doing these comparison statements instead of having a bunch of timers. You say, well, which is easier? It's your choice. It's your choice. So number 7 would be take the square root. How do you take the square root? SQRT, I think, but it's listed, and I'm going to let you do that. I'm going to let you do that. Okay, number 8, same thing. Number 9. How do you do number 9? Okay, so if you have the value of the accumulated value, and each one is worth 35 cents, how much do you find the total cost? Well, if you're an Allen Bradley, it's a compute block. If you're Siemens, it's a calc block, but it does the same thing. It's Allen Bradley, Siemens. So you can do it as a multiply block or as a calc block, and I like the calc and the compute block because it's pretty simple. So with the compute block, you write it in here as an expression. Widget count accum times 0.35, and then it comes out here as the total. With the calculate block, you have ends. So I have N1 and N2. And N1 is my count accum. And my N2 is 0.35. And my expression is N1 times N2. And my output over here is total cost. Either way. Number 10, interesting question. You may only use contacts and coils. But I have an integer here, and I want to know if the integer is equal to 22. So I have to divide this integer up into its component parts. So basically I look at an integer and I say 22 is what? It's equal to 0 times 2 to the 0. Okay, so let's just see what it's equal to. It's equal to 16 plus 4 plus 2. So it's 0 times 2 to the 0. It's 1 times 2 to the 1, which is that one right there, plus 1 times 2 to the 2. 0 times 2 to the 3, which is 8. 1 times 2 to the 4, which is 16. So I look at this number and I say, well, if I had these bits on in this word, bit 0 is a 0, bit 1 is a 1, bit 2 is a 1, bit 3 is a 0, bit 4 is a 1, and the rest of them are zeros, I could express that. So how do I write this? This is the word called int underscore 1. That bit right there, if I'm in Allen and Bradley, is int underscore 1 dot 0. If I'm in Siemens, it's int underscore 1 dot x 0. So if I write a string of bits saying int 1 dot 0, normally closed, int 1 dot 1, normally open, int 1 dot 2, normally open, int 3 dot, excuse me, int 1 dot 3, normally closed, int 1 dot 4, normally open, and the rest of them normally closed. That would give me an answer. That would give me my answer. So that gives me a way of checking the bits in a word without having to look at it as a number, or you can look at it as a number. Either way, you can look at it, and it works. So that gives you a little bit of an idea about how that's done. Okay, number 10. It's an averaging of three numbers, so you add the three numbers together, and then you divide by 3, and that's all you have to do. So again, would you use a compute block or calculate block, or would you use the adds and the mulls? I would use the compute block. That way you do it all at once. Okay, so number 12. We have a system here with 2 conveyors on it. And it may be a little bit difficult to see, but you have a counter that counts up. That would be the counter for conveyor 1. You have a counter that counts down. That would be for counter for, or you could put them all together, which is basically what this is about. So you physically have a counter with a count up and a count down, and the photo I1 does the counting up, photo I2 does the counting down. So this would be the Siemens counter. So this would be my storage count. And this would be my accumulated value here. Let's just call it accumulated value. CTUD. If I had this would be my Siemens. If I had an Allen Bradley, I would have a CTU, and I would have a CTD. Both with the same name, storage count. And I would get at my accumulated value by .acc. Either way, I would basically do the same thing. So then all my lights are is a comparison statement. So less than or equal to 0. Accumulated value, less than or equal to 0. That will give me my, you always want to test for less than or equal, because if you say equal 0, if it goes negative, you don't see it. So this would be my empty. My not empty would be greater than 0. My 50% would be greater than or equal to 50. %, would be 90. The number here would just change to 90 for 90%. For 100%, it would change to 100%. So that gives you some ideas about how to set up some lights based on this kind of an arrangement, either way. So that gives you an answer for number 12. Okay. So number 13 we're just going to skip. Number 14 is an interesting problem. For a deadband for like if you have if you want to turn something on when it goes above a certain number, let's call this high, call this low. And so you want to turn it off if it comes above this and on if it goes below this. That's the kind of thing you want to do. So when you go above this, you want to make this your set point. When you go below this, you want to make this your set point. So this is a oscillatory, but it's based on 2 greater than high. I set my set point as the low. Okay, I turn on, I do a set. And when I go below my low, I do a reset. That kind of thing. That's how that works. So you basically, this would be for cooling, or it's up to you. If you want to do it the opposite, it would be for heating. But that gives you an idea. Gives you how that would work. One of the ways that would work. So how does the two processors, Siemens and Allen Bradley, do this scale with parameters? Okay, so number 15 is the SCP instruction, which is the old instruction for scale with parameters. I'm going to deal with this again, but Siemens does a scale instruction and a norm instruction. We're going to deal with this again in chapter 10. And Allen Bradley, this would be Siemens. Allen Bradley does the configuration at setup time of the card. So they handle the scale with parameters very differently between the two. Number 16, how do you add 1% to a variable? Okay, so basically you know the full scale. Let's say the full scale is 1,000. What's 1%? Is what? 10? Okay, so if I have a push button here and it says add 1% to a variable, I just add 10 back to itself. What do you have to be careful of? That you don't go over a limit, right? That the var is less than or equal to what? 990, because you don't want it to go over that. So you're going to add 10. You don't want it to go above 10. You don't want to go above 1,000. So you have to guard against it going above that. But here's my push button. That adds 1% to a value. Number 17 has pretty much been worked in the book, and I'm going to let you do that. And number 18 has pretty much been worked in the book, and I'm going to let you do that. Number 19 is a type of problem that, again, this goes back to chapter 6, and I want you to get this. Chapter 6 how do you set a set reset circuit from a seal circuit? So this is a seal to set reset. Okay. So you look at the feedback portion of that circuit, and here's the circuit A, not C. Here's my feedback, F. Now here is something new, equals. This is the equal statement. And then this is D and not E. Give me output F. Where's the start part of the circuit? Right here's the start part, right? Where's the stop part? Right here's the stop part. So what do I do with the start part? Move it over as is. A and not C gives me my set for my bit called F. What about this part right here? You must take the De Morgan. How do you take the De Morgan of it? You negate each of these. So the equals becomes a not equals. D becomes ORed with not as a not D, and E becomes as is. So basically the reset becomes not D, E, and not equals that equals statement. So that gives me my answer for that one. Okay. So number 20 is a problem with going back and forth a set number of times, or until a weight equals a certain amount. So you go one side, hit a photo eye, time it, and then go back to the other side. And you keep doing that until you meet a certain weight in the box. So let's just call each of these passes a cycle. Each time down and back, a cycle. Okay, so I push the button, and it sets some kind of a seal circuit. It says run. So now that I am in the run mode, I start going right, run, and okay, so each of these is a, okay, so the run mode and okay, so I want to do a run and I want to start, and let's just say I want to go to the right. Okay, so let's just say on a positive edge of the run, I start the process to the right. Okay, so I go to the right. So that gives me a bit called moving right. So I set up and move right until I hit the photo eye on the right. Until I hit the photo eye on the right. And then I say at the end over here, then I have a time delay. And then I start back. And then I go to the left. And I set up a memory circuit for going to the left. And then when I hit a photo eye at the left, then I'm done with my first cycle. So this would be a cycle. And I'm going to let you finish this and then work at it. We're going to, this is a memory circuit but it also has to do with the scale. And when you get to a certain point, the scale says, no, you can't go any further, but you at least have to go all the way back before you turn it off. And that's how you would turn it off, is to scale is above, and you're done, turn it off, and then you drop it out. That's how that problem would work. Problem number 21, we just did one like, and I'm going to not do any more like that one. So basically I already set one up, and I'm going to let you do those. So this ends the problem set, and we're going to work on the lab next. So we're going to work on the lab. Okay, so with the lab, we have we're working with an integer, and we're taking the integer and we're splitting it into 16 bits. So you're going to define a word. Let's just call it word 1. Really an imaginative here, call it word 1. And we're going to add it to word 2. Okay, so we're going to add word 1 to word 2. We're going to add it not by using the add blocks, but we're going to add it bit by bit. So how would you describe how to do this? Well, you would look at the hints at the end of the chapter, and there are in the hints, it basically says, look at this, and you add this bit to this bit, and here's my result. So here's my result, 16-bit, 16-bit. But how would you describe that? Okay, so word 1 dot, I'm going to do the Siemens, this one, x0, and not word 2 dot x0 or word 1 dot x0 knotted and word 2 dot x0, give me result dot x0. So one but not the other. This one but not this one gives me this one. This one but not this one gives me that one. And this describes that. It's called a half adder. Now what else do we need? We need to know whether it's a 0 here because of a carry. So we need to know if there's a carry. So how would you do that? If they're both on, word 1 dot x0 and word 2 dot x0, give me a carry bit. Let's just call it a carry for right now. And that gives me a bit that I can use up here, right? That's exactly what that does. So now with that information, now we can go to the next bit, right? We can go through this, and we can now say what? Now we can build a full adder, because the full adder is what? You have a carry from the previous bit. And I think you see the process here, and I'm going to show you part of it, but I'm just going to tell you that it works. And it's in the book with the old style verbiage, but it's there. Okay, so with bit 1, what does it take to get a 1? Well, it takes 1 or 3, so basically word 1 dot x1 and not word 2 dot x1, excuse me, and not carry, or not word 1 dot x1 and word 2 dot x1 and not carry, or what? Not word 1 dot x1, not word 2 dot x1 and carry, or what? Or all three. If they're all three on, then you get a 1 as well, right? So all three give you what? Result dot x1. Okay. So that is the word result. And what if you have, now, what would it take for a carry? There's quite a few, there's a combination for that as well. Any two or all three would give you a carry, right? So word 1 and word 2, but not C, word 2 and okay, word 1 and word 2, word 1 and C, word 2 and C, or word 1 and word 2 and word 3 would give you a carry. So the carry for the next bit would be word 1, word 2, but not carry, or word 1, not word 2, but carry, or word 1, not word 1, but word 2 and word 3, and carry, or word 1 and word 2 and word 3. Would each of those would give you a carry. Now you say, what is this carry bit doing? It's the same as this bit here, but it's the next one that we rewrite it later after the original one. So this C is the same as the other C, but we would just say, if you're more comfortable, you could say carry dot x1 if you wanted to have a carry word, but you can just have a carry bit. It doesn't really matter. Your choice. And you do this for all 15 bits. Bit 1 through 15. Now bit 0 we already did, so you don't do that one. But bit 1 through bit 15 you do this way. And when you get to the last one, you get the reward. You don't have to do the carry. You don't have to do that at all. Okay, that's an add. Now, how do you do a subtract? Well, if you remember your 2's complement, you take word 1 and leave it alone. Leave alone. Word 2, you take the 2's complement. And then you add word 1 plus 2's complement to get result. So how do you take the 2's complement of a word? You take the 1's complement and add 1. That's one way of doing it. But the better way, the easier way to do it, is to look at the bit, and this is in your book, and if it is a 0 or a 1, you bring it down, starting at the right. So you bring it down. And you keep doing that until you hit a 1. You hit a 1, you do the flip. So when you hit a 1, from that point on, you do a flip of the bits. So you would not bring the bit down, you would bring the flip of the bit down. But you have to determine where that point is when you hit the first one. If this is your first one, you would flip after that. You bring that one down, and from that point on, you flip the rest of the bits. And that gives me my 2's complement. Okay, so how do you physically do this? Well, you set a bit to off. So I do a reset to the bit called flip. Then I move the bit x0, word.x0, over to 2's. Let's just call it TWO or just TW. .x0. If 2's .x0 is on, set flip. Then you do that one time. Then this rest of this, you do this 15 times. If flip is off, you move the bit word.x1. If the bit is on, you move it. If flip is on, you move it if the bit is off. And then if word.x1 is on, you set flip. You do this 15 times. This gives me my 2's complement. Now you say, why are we doing this? Well, you get good at copy-paste. You get good at a number of things. Plus, from this point on, you'll never see a number as just a number. You'll see it as 16 bits or 32 bits. But do this, declare these as 16-bit integers, and you'll be fine. So the rest of this lab, and lab 8, I'll explain using the TIA portal software. So I'm going to shut down the board, and I'm going to go to the software to do the rest of it. Okay, so we're now back with the lab 8, and we're looking at it from the Siemens system, and we'll just say we're starting from scratch, and we're going to declare words. So let's just type in this word, word1, and in the tag table, let's just see what we got. Okay, it's not a bool, it's an int. Start typing int, and we're going to say it's an m. Let's just go with m2. mw2. Okay, so we're going to start at mw2. That would be word. So that would be 2. So word 2 would be at int, and it would be at mw4. So then a result would be at mw6, and 2's complement would be at mw8. And what else do we need? We need, if you want to do the carry, you can. If you want to do it that way, you can. If you don't want to, you can decide how you want to do that, but there it is. And you want a word called flip, or bit, and that's a binary bool. And it's not an MW, it's an M12.0 or whatever, but that would give you a bit. Now, I want to show you how to modify these so you can actually check this program out using whole words. So I'm going to compile this. There's nothing in the program right now. OB1 is empty, but I want to compile this. I've defined some words in my tag table, but I haven't written the program. But I want to show you how to download this, that once you've got this working, and use the watch table to be able to see the actual answers. So the key is declare these as words, 16-bit words, ints, and then be able to address them like we did in the example, and then go on here to what we call a watch table. So you have to declare a watch table. You don't get them for free. You have to add a watch table. So now, if I want to watch a specific area, I can say, okay, word 1. Okay, so there it would be. Now I can look at it in all these different formats. I got to click on my glasses. So right now that word has a number in it. So I didn't know that, but it does. So let's just put it as the monitor value is 3. Now let's go over here and see what the modify value of it is. Let's just modify it to 50. Okay, let's put a modify value. So I want to modify that to another number. So I go up here to the lightning bolt with a 1 by it, and I click on that, and it should move it over. And it did. So if I want to put a number into a word, use the watch table and the modify value, and it will do that. And so you can check these out that way. I can put in a number into word 1, word 2. I shouldn't be able to put one into result because it would be, I would just see it. But there's my monitor, right? That's the value I have set right now. And you say, can I put a negative number in there? Yes, you can, as long as this display format is decimal plus or minus. So let's just put in a number 49. So it moved that number. Now the result would be 50 minus 49 would be 1 if I chose to do the subtraction. If I just chose to do the add, you can decide whether you want to do the subtraction part of this or not. But that would give you the ability. And what does this give you the ability to do? It gives you the ability to load up information using the watch table, or to be able to monitor and modify information in your program. So it gives you the ability to do a lot of things. The watch and the force table. The force table is right above it, but the watch table gives you the ability to put numbers in actively into a program and then see if they change or see what happens. And that's a good way of populating a program to see what actually can take place. But that gives you the idea of being able to change these numbers as numbers, even though you're doing the programming by bit. So this is the number. It should work. What if you say, well, if I put a negative number in there, doesn't matter, it will work. This is built to handle the 16-bit integer exactly the way that you wanted it. So again, what is a number? It's 16 bits. It's also a number. You have that now. Either you get that option. It's not just a number. It can be 16 bits as well. So take care, and hopefully this helps with the lab at the end of Chapter 8.